Hey, what's up, everyone? How are y'all today? Doing good myself. Doing good myself. A little tired. I'll survive though. Alrighty, so I am going to try to get through everything, the rest of the chapter today. Should be doable. Should be doable. And if we can do that, then I will give y'all tomorrow off. Just don't tell anyone. That'll be our little secrets. Okay. Yeah, if we can get through the rest of this chapter. Yep. Enjoy the weekend. No, actually not an April Fool's joke. Actually not an April Fool's joke. Actually serious. No problem. It'd be nice to have a long weekend myself. So, alrighty. Let's get rolling, shall we? Okay. So we're going to finish up talking about vector fields. Okay, so remember, a vector field is, so a vector field on R2 is a function from R2, right? So you assign to each point in your domain in R2 a two-dimensional vector. So we write them as usually capital F with a vector arrow over it. And we don't always write the XY because we're lazy, but it's a vector whose components are scalar functions of X and Y. Sorry, whoops, that one's not a vector, that's just a scalar function. So that's on R2 and on R3. To each point in the domain in R3, we assign a vector, a three-dimensional vector, each of whose components are functions of the point, scalar functions. Okay, so these are vector fields. So at every point, you're attaching a vector. You're assigning a vector according to the function. Okay, so we saw the del operator is, we think of it as a vector whose components are partial derivatives, whose components are the operation, take the partial derivative. So ddx, ddy, ddz, if we're in R3, or if we're in R2, ddx, dy. And we treat these just like normal vectors. And we can do operations that we normally do on vectors. So we can multiply this vector by a scalar function. And we saw, for instance, the gradient of f. You can think of that as ddx, ddy, the vector del, ddz, times the scalar f, which is the same as you bring, so a vector times a scalar, you just multiply each component by the scalar. And multiplication of a function by d dx is df dx, so on and so forth. So that's the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, which is, of course, the gradient, which we've already seen. But now we're going to see other things we can do with the del operator. And it's useful to think of it as a vector itself. Okay, so we saw the divergence of a vector field F. So we think of the vector field now as a vector, each of whose components are functions, and you take the dot product of that with the del operator. We saw that yesterday. And today we're going to see the cross product. So we call that the curl of a vector field F. And I want to emphasize needs to be a vector field on R3. This is only defined for vector fields on R3, not on R2 or R4 or anything else, just on R3. For the same reason, we can only take the cross product of three-dimensional vectors. We can only take the curl of a three-dimensional vector field. So the curl is just del cross F. So let's write out what that is. So our del is d dx, d dy, d dz. And our F, vector field F, is F1, F2, F3. So remember your plus minus plus. So we know how to take the cross product. I'll just write it out. So we get the partial of F3 with respect to y minus the partial of F2 with respect to z. Then we have the partial of F1 with respect to z, minus the partial of F2, F3 with respect to x. Or you can think of it as negative partial F3 with respect to x minus F1 with respect to z. But we just distributed the negative through. And then we get the partial of F2 with respect to x minus the partial of F1 with respect to y. So, I mean, like if you want, you could memorize this, you could notice some patterns, etc. But obviously, it's much more compact just to think of it as the del operator cross the vector field F. Much easier to think of it that way. So that's the curl of a vector field. Okay. So let's calculate the curl of the vector field xy e to the x y plus z. Nope, not z plus c, y plus c. Not curl or, curl of. Okay. So the curl of our vector field is, of course, del cross f. So del is d dx, d dy, d dz. And our vector field f is xy, e to the x, y plus c. Let's do our plus minus plus. Okay. So remember cross product. Cross out, start with I, cross out the row and column containing I. Then do d dy times y plus z. What's our d dy times y plus z? Remember, multiplication is just take the partial. So what's the partial of y plus c with respect to y? Just 1. And then minus d dz times e to the x, which is 0. So then minus d dx times y plus z, which is 0, minus d dz times xy, which is 0, and then plus d dx times e to the x, which is e to the x, minus d dy times xy, which is x. So we go 1, 0, e to the x minus x is the curl. Okay. So it's kind of weird, actually, describing what exactly curl is physically. But if you think of your vector field, so think of your vector field as giving the water velocity. Oops. So right, you have a, or let's just say fluid velocity, whatever. You have a flowing fluid. Yeah, water velocity is fine, whatever. So I think of a current, right? At each point in the water, you can look at the velocity of the water at that point, how the current's flowing, right? So if your vector field gives you the water velocity every point, so we'll call that F, the vector field F. So at a point, if you orient a tiny paddle wheel with axis pointing in the direction of curl of F at a point, so you got moving water, we have a little paddle wheel, right? There's our beautiful little paddle wheel. Here's our axis, right? So you put it at a point, it's a little tiny paddle wheel, and you orient the axis in the direction of curl of f. Then the rate at which it spins is given by the magnitude of curl of f. So curl of f is a vector, magnitude of curl of f. That's going to give you the rate of rotation. So if you orient your paddle wheel like this, and the current tends to make it spin around, how fast it's spinning is going to give you the magnitude of curl of f. Usually not what we're thinking in our head with these problems, but that's the physical meaning of curl of f. So in particular, if curl of f is a zero vector, that means the magnitude of curl of f is zero. And so that means however you orient your paddle wheel at this point, it's not going to rotate, right? So we say the vector field is irrotational. So if the curl of f is zero everywhere, we're not going to use the word irrotational too much, but yeah, that has some physical ramifications, and there are a lot of important vector fields, as we'll see soon, with that property. But yeah, that's what curl of f means physically, but I wouldn't worry too terribly much about that. Okay, so let's switch gears a little bit and look at conservative vector fields, which are very important. Yes. Okay. So we say a vector field, it can be either a vector field on R2 or a vector field on R3. So we'll leave it ambiguous here. So we say a vector field F on R2 or R3. We say it's conservative. And we're going to be coming back to conservative vector fields a lot. So we say a vector field F is conservative if there is a scalar function little f for which our vector field big F is the gradient of little f. So in other words, conservative means you're the gradient of some function, some scalar function. So remember we said the gradient of a function is a vector field, right? You get a vector, each of whose components are the partial derivatives. So each component is a function. So a gradient is a vector field. They're very important vector fields. And so basically, if a vector field is a gradient of some function, if there's some function you can find where you take the gradient and you get this vector field, we say this vector field is conservative. So little f is called a potential function. So little f is not unique, right? You can always add a constant to it or something. You can always add a constant to it and still, you take the gradient, you get the same thing. So little f is called a potential function. And this is not, I'll be referring to it as an antiderivative because it'll be useful to think of it as such. So we think of little f as an antiderivative of our vector field, f. I'll be referring it to that as such in the future. But yeah, you're conservative if you're the gradient of some function. Not every vector field is conservative. Most are not. But the ones that are very nice, have very nice properties. Yeah. Okay. So, for example, if we have the vector field y, x plus z squared, 2yz, that is conservative since it is the gradient of the function so if we look at the function xy plus yz squared, so that's a potential function for this. Right? If you take this guy and you take the gradient, right? Remember the gradient, the first component's the partial with respect to x. So we do that, we get y plus 0, so y. Second component is the partial with respect to y. So we get x, and then plus z squared. And the third component is the partial with respect to z, which is 0 plus 2yz, which is exactly what we got out there. So we'll look at later how we can find these scalar potential functions given a vector field. If we know it's conservative, we'll see in just a sec how you can check that it's conservative also. But we just kind of pulled this out of thin air here. But we'll see in the future how we can find a potential function if we know a vector field is conservative. But yeah, this is a conservative vector field because it's the gradient of this function here.
Did you know that that was conservative just like off the top of your head, or like you were just showing us an example?
I could eyeball it now and tell it's conservative. What we do essentially when we so there's a way we'll see in just a sec that you can check really quickly that a vector field's conservative. But you can kind of figure out that it's conservative without doing that. So we know if it's conservative, first component's the partial with respect to x, second's partial with respect to y, third's partial with respect to z. So integrate the first with respect to x, second with respect to y, third with respect to z, and kind of splice everything together and see if you can find some function. We'll talk more about that, but yeah. You'll be able to tell pretty quickly if you get good at it that it's conservative. So that's conservative. But if I just pick any old vector field, it's probably actually, we'll do an example in a second. Most vector fields are not conservative, right? It's a special thing to be conservative. Okay. Alrighty. So how do we tell vector fields are conservative? Well, there's a test we can do which shows that they are conservative. Or if a vector field is conservative, it'll pass this test, and we'll see some more stuff to do the other way around. So we have two different tests depending on whether we're a vector field on R2 or a vector field on R3. So on R2, so our vector field F1, F2, sorry, let me phrase this better. If our vector field F1, F2 is conservative, then the partial of F2 with respect to X will be equal to the partial of F1 with respect to Y. So we sometimes call this the cross partials condition. So in R2, you can check quickly that a vector field is not conservative by doing this check. So take the second component, take the partial of the second component with respect to X, the first derivative, or the first variable, and the partial of the first component with respect to Y, the second, so the cross, and see if they're equal. If they're not, then you can't be conservative. But if they are equal, they're conservative with some other conditions, but we won't get into that right now. Okay, so in R2, if your vector field is conservative, then it's going to satisfy this cross partials condition. Partial of the second with respect to X is equal to the partial of the first with respect to Y. So in R3, if our vector field F1, F2, F3, oops, is conservative, then the gradient of our vector field, no, not the gradient, oh my goodness, sorry, the curl of our vector field is going to be the zero vector. So you need to remember this, because we'll be often checking in many problems whether a vector field is conservative. And this is a quick way to check. Right, so if we're in R2, do the cross partials thing. If we're in R3, see that the curl of F is 0. So every conservative vector field, the curl of F is 0. So if the curl of F is not 0, you can't be conservative. Okay, so let me show you why the first one is true. The second one takes a little longer to show, but it's not too hard to do. So the proof for the first one. Okay, so suppose our vector field is conservative. We're going to show that it satisfies the cross partial condition. Whoops. So our vector field F1, F2 then it has to be equal to the gradient of some function, f for some potential. So I mean, our vector field needs to be, the first component's the partial of the potential with respect to x, the second is the partial of the potential with respect to y. We don't necessarily know what f is, the potential function. But we know there is some where if we take the partial with respect to x, we get f1, and if we take the partial with respect to y, we get f2. So then, the partial of f2 with respect to y is the partial with respect to y of f sub y, where little f is our potential. Oh, sorry, x. I wanted x here. And when you take the derivative with respect to x of f sub y, you get f sub yx. And then similarly, the partial of f1 with respect to y needs to be the partial with respect to y of f sub x for whatever our potential function f is, and that's f sub xy. And we know by Clairaut's theorem, these guys have to be equal. And so that means that the partial of the second with respect to x has to be equal to the partial of the first with respect to y, if we're conservative. So that's why that cross partials condition is satisfied. Okay. So we looked at this guy earlier, yx plus z squared 2yz. So let's verify. We said it's conservative. So that means when we take the curl, it needs to be 0. Let's verify that that's the case. Sorry, it was yx plus z squared. Two yz. We showed earlier it was conservative. We found a potential function. So let's check the curl of f. So curl of f is del cross f, which is, so del is d dx, d dy, d dz. And f is y, x plus z squared, 2yz. So do our plus minus plus thing, and then let's check. So so d dy times 2yz is 2z, minus d dz times x plus z squared, which is also 2z, so that's 0. So minus d dx times 2yz, which is 0, d dz times y, which is 0. And then k times, so d dx times x plus z squared is 1, minus d dy times y, which is 1. It is indeed the 0 vector, like the theorem says it has to be. Okay. So let's look at another vector field and see if that's conservative. So is our vector field xy, x squared over 2, zy conservative. So we'll see later that the theorem works both ways. So the way we wrote the theorem, it just says, if we're conservative, then it's going to satisfy these conditions. We'll see later that we can actually say, if it satisfies those conditions, then it's conservative, right? So if we want to know that a vector field is conservative, if we're on R2, we check the cross partials. If they're equal, it is conservative. And if we're on R3, if the curl is 0, then it's conservative. But let's do it in this case. Let's check the curl and see if we get 0. If we don't get 0, it can't be conservative. So del cross F, really quickly. So we get xy, x squared over 2, zy. Okay, so we get ddy times zy, which is z, minus ddz times x squared over 2, which is 0. You can stop right there. First component's not equal to 0, so we already know we're not conservative. But we'll go ahead and check the rest. So we get ddz times xy, which is 0, minus ddx times zy, which is 0. So that's 0. We get ddx times x squared over 2, which is x, minus ddy times xy, which is also x. So our curl is z, 0, 0, which is not the 0 vector. And so since the curl is not 0, our vector field is not conservative. If it was conservative, the vector field, or the curl, would be 0. And let me okay. So, and then just one more quick theorem before we leave. We'll talk more about conservative vector fields in a couple chapters, but so remember we said a vector field is conservative if it has a potential function. If there's some scalar function, little f, where when you take the gradient of little f, you get our vector field. If that's the case, then we're conservative. Is little f unique though, right? Are there multiple potential functions for this guy? Are there multiple different scalar functions where when you take the gradient, you get this vector field? Well, it turns out kinda, but they only differ by a constant. So every antiderivative is just one of the antiderivatives plus a constant. So it's like a normal antiderivative thing. They're all the same, just plus some unknown constant. So for vector field F, it's conservative. And we'll probably talk more about this later, but it's in fact not, it's always going to be true in this case. So it needs to be conservative on an open connected domain. That's always going to be true in this case, but open means it contains open means around every single point in your domain you can do a little ball, and all the points in that little ball are in there, and don't worry too much about it. And then connected means you can draw a path entirely in your domain between any 2 points in the domain. So it consists of like one piece, essentially. So then so in other words, any 2 potential functions differ by a constant. So basically your antiderivative, right? Your potential function is unique up to adding a constant to it. Just like normal antiderivatives. Okay. Any questions about anything we went over today? Alrighty. So that does it for today. And we finished off the chapter. So you know what? Have a nice Easter weekend. And don't bother showing up tomorrow, because I won't. Anyways, I'm going to move over to, I'm going to move over to my office hours. And I'm going to start grading exams today. And hopefully I can get that done today. But yeah, have a nice weekend. And I will see y'all again on Monday. Later, guys.